Buenos días.
Hola, ¿qué tal? Buenos días.
Bueno, Freddy, podemos empezar. Si quieres hacer un conteo de 5 segundos para mandarte al aire. Hola, Freddy, ¿cómo estás? ¿Me escuchas?
1, 2, 3.
¿Me escuchan todos? ¿Me escuchan todos?
Sí, yo te escucho.
Ok. Entonces,
4.
Freddy, vamos a hacer un conteo de 5 segundos para que tú le des la entrada a Arián y yo mande del logo a usted. ¿Ok?
¿Pero lo conteo en voz alta?
Sí, debe contar en voz alta. Cuando ya usted llegue al 1, yo lo mando enseguida. Y empieza.
5, 4, 3.
Recording in progress.
2, 1.
Listo, ya puede empezar a hablar.
Bueno, buenos días a todos.
Good morning, everyone. This is the second session of technical conferences in this 7th International Ship Design Enable Engineering. This morning, we're going to have 3 talks focused on aspects of design for vessels, and we're going to start with this initial talk entitled Analysis of the Angle of Incidence of a Rigid Sail for using dragging forces on a catamaran type boat. Mr. Adrián Terán Castañeda from National University of Engineering from Peru. He has experience in computational fluids, and he is going to be doing his talk this morning. You have the floor. Okay, thank you so much for this introduction. That is my background. First off, I would like to thank you for the opportunity of doing this presentation in COLOMBIAMAR, and we're going to start with the topic, which is the analysis of the angle of incidence of a rigid sail on a catamaran type boat. My name is Adrián Terán Castañeda. This is work that I carried out with some of my peers at the National Peruvian Engineering University. And to begin with, by giving some of the context of the analysis, we need to look at the goals of IMO in terms of the reduction of greenhouse gases. One of the objectives is that by 2050, a reduction of at least 50% of greenhouse gases given off by vessels can be reduced. In order to achieve this objective, IMO has set out on different projects and operations. In this case, in this graph, we can see the first line, which is black dotted line, which presents the current scenario up to 2050, without taking any action for the reduction of such emissions of tons of CO2. And then we have several strips, such as the blue one, the orange one, that indicate reductions of the CO2 being given off into the atmosphere. The first one is the EED, which is the energy emission reduction, which is applied to new vessels, restricting the amount of carbon dioxide per mile of vessel capacity in terms of emissions. So as long as that EEDI is lower, the impact from the vessel is going to be lower. The other one is SEEMP, which is Energy Efficiency Management Plan for the vessel. It is an operational measure which actually also improves the efficiency of the vessel in a profitable manner. With these blue and orange strips, we reach a considerable reduction of the CO2 constantly being emitted by vessels. However, there is a huge gap to be covered, which is the green strip. That gap has got to be covered by means of technological innovations, both in terms of fuel and new technologies. An example that we can display here could be residual heat recovery systems, gas recovery, fuel cells, new hull designs, with improvements in terms of propellers and also the use of renewable energy such as sun and wind, which are specific of this presentation. Okay, having explained the objective and the context in terms of energy efficiency, we need to analyze the various types of hulls that we can utilize in this case. It is going to be a high-speed hull, which can be categorized in terms of the shape of the hull, the number of hulls, such as a catamaran that has 2 hulls or a trimaran that has 3, and the type of equipment that the vessel has in this case. It could be by buoyancy or hydrodynamic, and some vessels actually use both. However, for the case of study, the vessel selected and the type of hull selected is that of a catamaran. We know that there are some advantages which are quite good when it comes to using a rigid sail. This is due to the fact that the catamaran hull, which is the one we see at the bottom of the picture, splits the total displacement of the vessel into 2 areas because it has 2 hulls. That results in stability improvements, and thus the vessel can achieve high speeds at very small angles. Why is this important? Because when we use a rigid sail, in this case, there's going to be a component generated by the wind, which is going to make for the unit to list. This can actually be advantages when it comes to the operation of the ship. Now, in terms of the case of study, this is design inspired by a European cargo express vessel, which is very peculiar. As you can see on the screen, it has a rigid sail, which is shown in blue in the presentation. And that rigid sail has different functions. In addition to improving energy efficiency by means of the wind, but it also has a solar panel deck for using this kind of energy. This is a container carrier where the sail also operates by covering the containers if that's necessary. Also, when the vessel arrives to port, it can also serve as a crane. So it adjusts to the needs and the type of operation for this vessel. The main characteristics that we can find, and some of which are going to be quite useful when it comes to the analysis, is the total length, which is 85 meters. Another important characteristic, in addition to the ones you can read from the screen, is the operational speed, which is about 13 knots. In the operational area of this vessel, there is a condition of a wind. It is perpendicular to the speed at which the vessel is navigating, particularly the bearing of approximately 30 knots. That's also important because it is the case of analysis for the design that's been made. Now, we have to talk a little bit about the types of sails available that can be applied to the vessels depending on the use, the type of use required. These sails have streamlined characteristics that can be used in different types of wind. This is used for calculating the production from them according to the operating speed of the vessel and also the wind speed. So the different types of data have to do with the coefficient of drag of the sail, and that's what the analysis is focused on. So as follows, I'm going to show you the forces that are going to be acting upon the sail. The rectangle, which you can see, is a representation of the vessel, which is indicated by number 1. While the sail is indicated by number 2, is the semicircle that we can see there. We have the operational speed that can be seen on the screen. It is within the vessel, and We also have the speed at which the wind is going to move, which is perpendicular to the direction, to the bearing of the vessel. On the basis of that speed, we're going to acquire an apparent wind speed through which we'll analyze the performance of the sail. Given the interaction between the fluid and this structure, some forces are going to come up, such as force of sustenance and drag. Now, as we consider these forces and in the directions that we want to analyze, which is basically the bearing of the vessel in a perpendicular direction, we're going to be able to see a drive force that goes in the direction of the vessel and a force alongside. That is the force that gives the vessel a list. If the angle is too high, the integrity of the vessel may be at risk, as well as the vessel's performance. That's the advantage of using these kinds of catamaran hulls. Now, as for the sail that we are utilizing, the main characteristics in terms of height, basically 67 meters of height and a width of about 19 meters and total area of about 1,900 square meters. Now, we also need to talk about the analysis that is being made on the whole set of the vessel, given the fact that, as I mentioned previously, in order to use a sail, we need to use a wind tunnel. In a similar case, to analyze a hull, we've resorted to the analysis of a hydrodynamic tunnel to analyze the case. However, by analyzing the joint performance of the sailboat is a little bit difficult, a little complicated because of the conditions of the sail at the speeds that it is going to be operating at. Therefore, amongst the alternatives that we can find, there is a CFD analysis, which is computational domain analysis, which is very relevant and very convenient for this case. Now, in this analysis, what we normally do is, instead of the ship moving at a certain speed on a given space, such as a tugboat channel, we can create a working domain, which is going to be called a computational domain, where the whole of the ship is going to be printed at a prudent distance from the bow, a water inlet where the vessel is operating. There is also a water and air outlet, and towards the side, we create the walls. Now, how large does this domain have to be so that we can carry out the calculation? The ideal situation, according to the recommendations of the ITTC, the domain should be large enough so that phenomenon occurring around the hull, the formation of waves, is not disturbed by such walls. So we have created the domain for this analysis on account of the whole length of the vessel, which is 85 meters. Okay, the size of this unit, as we have seen, depends on the length. The shape is a little bit peculiar. That is due to the fact that the air inlet is going to have two components. One is going to be the vessel navigation speed, and then the wind speed will require a curved air inlet so that we can capture these two components. We cannot provide a flat air inlet, as you can see here. This is actually a particular factor of this analysis. Another peculiarity is the condition of no symmetry. On a tugboat, there is a symmetry condition, both geometrical as well as in other phenomena, which is a midship line, both port side and starboard side. In this case, we cannot do this because the sail is going to be analyzed from different angles. Therefore, that breaks the geometrical symmetry. If the sail has been displayed or deployed, we could have a geometrical symmetry, but not phenomenon symmetry, because the wind is going to provide another component. So these are some of the particular conditions, and we've divided the domain into two parts. One air, the other water, to control these air and water inlets and be able to generate the analysis. Okay, as for the boundary conditions, these are the conditions I mentioned before, the air inlet, which is the speed, which is the operational speed of 13 knots, and the wind speed alongside, which is about 30 knots. The water inlet uses a pressure boundary, which can be contradictory, but that's due to the fact that we have to enable an option, which is known as open channel, which allows for a larger depth of the water during the analysis. The turbulence model used is the pressure model, which can be carried out. Looking at the literature, it provides good performance when it comes to analyzing different types of vessels. Now, as for the outlets, the pressure outlet, as for the air outlet, we only use the atmospheric pressure. And for the water outlet, we also establish a level of reference with a zero-free surface and a depth of 85 meters. Now, a very important condition that should not be overlooked is the wall conditions at the top, at the bottom, and actually top, bottom, and side of the domain. On those walls, there is a constant stress of 0, so that there is no gradient or a boundary layer on these walls. Basically, the walls have to slide, and so that there is an interaction between the walls and the phenomenon of interest. The hull should be normal without any sliding, and the surface should come down to 0. Now we have some of the most essential parts, which is the grid of the domain, or the mesh for the domain. We have some polyedric, hexaedric, and prismic elements. The selection of these elements is due to the high quality of mesh that we can get as compared to other elements. In this case, we can see the elements on the external parts of the mesh. So later on, we can transition to hexaedric elements, which are the cubes that you can see on here. And finally, we can approach the surface both of the hull as well as the surface of the rigid cell with a prism layer that's used to be able to capture the effect of the boundary layer that is going to be generated around the surface. Of course, these mesh are of high quality. They can be measured. The main metrics have to do with a value between 0 and 1 for the mesh. These metrics are supposed to be at 0.15 ideally, and so forth. Around the mesh, the metrics will vary depending on the elements. The lowest values can be reached as long as prism elements are used, which is always necessary, particularly within these kinds of phenomena. And that's why the metrics is low at some elements, 0.08 for water and 0.05 for air. Now, this metrics does not mean that the design will not be satisfactory or that it cannot be carried out, but possibly we can find some errors and improvements have to be made. But given the computational conditions, we have worked with these metrics and we have achieved results that are coherent to the objectives that we're trying to accomplish. Okay, I am going to explain some of the refinement zones, which is the air-water interface with different prism elements that capture, as we will see in some pictures, the surface of the air-water interface without increasing the computational cost too much, because the types of finite elements is not very high when we are using this type of elements. Besides, to be able to capture or depict the free surface, we use the BOF model, which adds another variable to the cells where we're making all of the calculations which actually represent the fluid within each cell. In this case, a 0 value will indicate that the cell only has air, represented by blue. The value D1 is going to represent that the cells only contain water, represented by red. And to plot the free surface, we will use a value of 0.5, which is a case where the cell contains 50% water and 50% air. Finally, as for the results that we've obtained, we have the formation of waves, as we can see in the color white, going down to dark blue. This is the typical pattern that we have seen and that we have waited for. This is the results of the analysis at an angle of 0 degrees. We're also plotting the pressure rates on the sail, in this case, which we can see on the picture all across the rainbow range. In red, we have the highest pressure levels. That's due to the fact that the water entry is to the starboard side, to the port side, sorry. And we have to see the final analysis in terms of pressure and if it's actually beneficial for the case of study. This is the representation at the angle analyzed, which is 30 degrees. It is also within the expectations. Also, on the port side, there is higher pressure. There are areas of lower pressure because of the detachment of vortices that can be found within this blue area on the sail. And finally, at 60 degrees, this is the result that we have been plotting, and which shows the behavior of this rigid sail in the speeds of 30 and 15 knots, respectively, in terms of the wind speed and the vessel speed.
Al momento de realizar los análisis, hemos encontrado que la fuerza generada por la vela al ángulo de 60 grados es mayor. Esto tiene sentido dado que está casi paralelo al ángulo de incidencia con que llega el viento, con lo cual se encuentra la mayor ventaja del uso de la vela en este caso, a 60 grados, que es lo máximo que podía rotar. Y sin embargo, se puede encontrar cómo hay beneficios tanto desde 0, 30 y 60 grados para poder desplegar la vela y encontrar una reducción de el combustible necesario para el movimiento de la nave. También un análisis un poco más detallado, enfocado más en la vela, descomponiendo las fuerzas que actúan sobre esta, vamos a encontrar que la componente por presión es la componente predominante en cuanto a la fuerza que ayuda a la embarcación a navegar. En este caso, que es una componente positiva porque reduce esta resistencia al avance. Y la componente viscosa es una componente negativa que, sin llegar a ser despreciable, es muy baja en comparación con la componente de presión. Por lo tanto, una de las conclusiones es que la componente por presión la que más ayuda en el fenómeno, y pues estos serían los resultados obtenidos dentro de las simulaciones y el análisis. Por supuesto, se espera mejorar más adelante estos análisis contrastándose tanto en una prueba de canal para validar el análisis CFD, además de poder realizar más simulaciones a distintos ángulos para completar mejor una curva que muestre con más detalle el comportamiento de esta vela. Eso sería todo por la presentación que les tengo preparado. Espero que haya sido de su agrado y si tienen alguna duda con respecto a esta, me gustaría poder aclarárselas. Estoy atento a sus consultas. Muchas gracias.
Muchas gracias, Adrián, por tu presentación. Muy interesante tu trabajo. Tengo aquí algunas preguntas que nos han llegado para ti. La primera tiene que ver con con la última parte de la presentación que hablaste sobre lo relacionado con la reducción de la energía requerida para la propulsión de la embarcación. La pregunta está relacionada con si se ensayaron diferentes geometrías de velas para investigar su efecto en la reducción de la resistencia al avance.
Esa es una pregunta muy interesante porque da pie a la optimización en cuanto a la forma de esta vela. Lamentablemente, por temas de coste computacional, no se puede realizar simulación con diferentes perfiles, pero sí sería bueno poder tratar de optimizar esto. Sin embargo, hay que recordar que en este caso particular, la vela no sirve únicamente para mejorar el rendimiento de la nave, sino que cumple una función de grúa. Esta función es primordial para las operaciones que se realizan, por lo que en principio se tiene que cumplir un poco con esta necesidad de grúa y después tratar de adaptar la forma para que tenga un buen desempeño al momento de realizar el despliegue de la vela, para que funcione mejor con el viento. La respuesta es no se ha hecho un análisis, pero sería muy interesante hacerlo, tratando de optimizar la forma sin perder esta característica de la grúa.
Gracias. Otra pregunta es si tuvieron algún tipo de problemas de convergencia en las simulaciones y cómo los pudieron resolver.
Por supuesto. Las simulaciones computacionales, en este caso con Cfd, tienen bastantes variables que hay que controlar y hay que tratar de mejorar. Una de las cuales fue el mallado, por supuesto. Para poder lograr esta convergencia y para poder mejorar un poco, probamos con distintos modelos de turbulencia. Al final en la literatura encontramos que el KH no realizable, como mencioné, daba un buen desempeño y fue uno de los que ayudó a poder obtener resultados de forma precisa. Además de que al momento de hacer el mallado, nosotros estuvimos probando con distintos tipos de elementos. He mostrado los elementos poliédricos, pero también están los tetraedros o también mallar únicamente con hexaedros, el dominio del casco. Pero el problema es que en estos la cantidad de elementos se disparaba a más de 3 millones, un poco más. Por lo que no se podía realizar la simulación, directamente no se podía realizar por la cantidad de elementos. Entonces, una de las restricciones fue esas para poder encontrar la solución, encontrar un tipo de elemento que no dispare tanto la cantidad de volúmenes que se están analizando, dado que ni siquiera podemos colocar la condición como ya lo expliqué. Fueron principalmente esos los problemas. Encontrar un tipo de elementos que no dispare la cantidad de los mismos, poder hacer el análisis y el modelo de turbulencia adecuado para poder realizarlo. Fueron los principales retos y las principales cosas que pudieron haber afectado a la convergencia.
Perfecto, muchas gracias. Nos preguntan cuál fue el tipo de herramienta computacional que utilizaron, cuál es el software con el que trabajan y adicionalmente otra pregunta es cómo manejaron el tema de la definición del espesor de la capa prismática, si tienen algunas recomendaciones o criterios para la definición de Y+.
Por supuesto, ese parámetro no lo tocó mucho, pero es un parámetro bastante importante el de Y+. En cuanto al solver y el programa, hemos utilizado ANSYS Fluent. Esto porque nos permitía realizar el tipo de mallado poliédrico, como les he mencionado. Tiene unas opciones dentro del solver muy buenas, con las cuales podemos mejorar incluso la ortogonalidad del mallado fácilmente. Fue cuestión de probar un poco hasta poder encontrar ese mallado con poliedros. Fue dentro de ANSYS Fluent. En cuanto al Y+, por supuesto, es un valor muy importante al momento de estar usando funciones de pared, que es lo que se utilizaba en esta simulación. La recomendación que yo te doy es usar justamente las recomendaciones que da la propia ITTC, que para poder estimar este valor se utiliza la eslora entre perpendiculares, si no me equivoco, y te da una fórmula ahí con la cual tú puedes estimar. Una vez tú ya lo tienes estimado y generas la capa de prismas alrededor del cuerpo, tienes que hacer un testeo de cuánto es el valor de ese Y+ en todo el cuerpo, ¿no? Porque te recomiendan usar funciones de pared con este tipo de modelo que esté entre 30 y 100. Entonces, una vez que logras que esté entre esos valores, ya puedes estar tranquilo de que la simulación, los resultados de los esfuerzos que vayan a ver, pues van a ser correctos.
Bueno, muchas gracias.
Okay, thank you very much, Adrian. Those were all the questions. Thank you for participating in the Congress. And now we are calling all members for the next presentation in the next conference, next talk, in, in, in charge of David Carvajal. In the meantime, thank you very much.
Y un saludo a todos. Muchas gracias.
Gracias.
Listo, entonces 5 minutos.
5 minutes. Thank you very much, Adrián.
Gracias, Adrián.
Muy bien.
Muy buena presentación.
Excellent presentation.
Muchas gracias a ustedes. Nos vemos.
Thank you very much.
Me retiro de aquí.
Vale.
Listo. Buenas tardes, David, ¿cómo estás?
Good afternoon, Mr. David. How are you?
Buenas tardes.
Good afternoon.
Poner la diapositiva para ir acomodando sus escenas.
Turn on your camera in order to upload the slides.
David,
Dile, David, dile a Liberto que se escucha hasta acá.
Sí, señor, ya le digo por el capitán.
Sir, I'll tell him.
David. David,
Ya regresa. ¿Está?
Yes, sir.
Iban a ser cinco y hablando con mi coronel Vázquez, no, pues. Iban a ser 5. Sí. Pues puedo explicarle perfectamente que lo puedo hacer.
buenas tardes, David, por favor.
Sí, señor.
Good afternoon, David.
Ya comparto la pantalla. Sí, me escucha.
I'm going to be sharing my screen right now. Are you listening to me? Please take off your mask.
Pantalla.
Y si puedes bajar un poquito la
And
pantalla.
if you can move down the computer of your screen, so
Listo.
thank you.
Buenos días.
En vivo.
Good morning.
Buenos días. Seguimos. Soy Freddy
Okay,
Zárate.
we continue. My name is Freddy Zárate. I'm the Director of Naval Engineering at COLOMBIAMAR.
Técnica del día.
I welcome you to the second day of technical talks on design of ships.
Conferencia del día nos acompaña
In the day's second conference, we're going to have David
ingeniero mecánico
Alvarado. He's a mechanical engineer with a master's degree
especializado en impacto
in mechanical engineering from Universidad de los Andes. He
como auxiliar de
works on fatigue and composite materials, and right now he's working for the design division at COLOMBIAMAR. This morning he's going to talk about the design and validation by the finite element method of the structural arrangement of a riverine low draft combat boat. Okay, David. Good morning, everyone. It's an honor to be online with all of you, and this time around, I am honored to introduce the work entitled Design and Validation by the Finite Element Method of the Structural Arrangement of a Riverine Low Draft Combat Boat. This work was done alongside engineers Edison Flores and Edwin Paipa. Okay, first off, we're going to do an introduction and the definition of an engineering problem, so that later on we can continue with the methodology, the results, and finally conclusions and references. Okay, within the framework of the constitutional missions of the National Navy, there is the maintenance of territorial sovereignty in river or inland waterway regions. The high richness of the nation in terms of secondary and tertiary rivers, leading to lush jungles as well as isolated populations, lead to the need of generating a boat that is light but also resistant to patrol rivers, which actually go 30 centimeters deep in very severe climate conditions. Okay, in terms of the requirements, we have the low draft combat boat, SVCV, which has been designed to provide security to the crew because it includes polymeric armored panels with a cargo capacity of about 400 kilograms and a reach of 300 kilometers. The hull is totally made of naval aluminum. So we developed a vessel whose total displacement is about 3.6 tons with a total length of 8.6 meters, a width of 246 and a draft of 35 centimeters. As we said before, this vessel is totally made of aluminum, which makes for certain advantages, such as the boat being light, the weight resistance ratio is favorable, and a higher resistance to shocks and collisions, given the nature of aluminum, which is very pliable and very strong, as well as easily maintained. All of this coupled with the fact that the boat has fiberglass components. Given the fact that a light boat is required with low draft and with enough resistance to complete operations, the development of this project is to build this boat by following the classification rules, particularly those of ADS, ISO 12515. In addition to this, we should be able to validate the results in terms of structural dimensions and design obtained by means of standards and a direct analysis, which on top of this is going to allow us to improve the general arrangement of the vessel. Okay, the methodology basically is divided into two parts. First, we're going to have the scantling, which is an iterative process, which begins with the basic characteristics of the vessel to calculate vertical speeds as well as design pressures. Of these design pressures, and given the separation between longitudinal and transversal elements along the liner. We can determine the thickness of the liner, and then we make the calculation of the transversal component in terms of reinforcements. And finally, we do an analysis and a calculation of the midship, which should exceed the considerations given the standards. Now, on the basis of the model that we found and the design structure, we move on to a direct analysis, which is made up of 3 stages. The first stage is a structural analysis of the vessel by means of finite elements so that we can move on to a model analysis to look at the effect of vibration, especially in the mirror region, in terms of the behavior of the vessel, and to verify that none of the elements of the boat may fail because of compression instability. Now, firstly, there are materials. As I said before, aluminum provides us with a light vessel with a high weight resistance ratio, but there is a problem with high temperature gradients from welding. Its mechanical properties, in some cases, are reduced down to half. For this boat, we have 2 types of aluminum. 5083 H321, which is hardened aluminum, and aluminum of the 6000 series. H321 is used on plates, bulkheads, liners, decks, and frames. And the aluminum profile of the 6000 series is used for the profiles. According to the research, the effect of temperature is a local effect very close to the welding regions, and that the 5083 steel has a limited effect. It doesn't go lower than 50% of the mechanical properties, which is different to what happens with profile steel, which is very sensitive to temperature. The 6000 series is actually better because it can be bent and used as profiles because they are extruded. Now, as for properties for the model, we have density, we have the Poisson's ratio, and we can see that in aluminum 5083 H321, we have a fluent stress of 320 megapascals in unwelded condition. And in the welded condition, it goes over 346 megapascals. When we have aluminum, which is extruded, it goes from a fluency stress of 260 up to 125 megapascals. With these kinds of considerations, we move on to the next slide where we develop the computational design. Now, this model is a global model that is constituted in terms of plates, which was generated at the Space Claim 2019, and whose elements are bonded because they are, and the welding restricts the different degrees of freedom of the vessel. Now, the meshing, we use shell 181, ideal for surfaces for this kind of thickness and with quadrilateral elements, and the triangular elements are only used as filler. As for the boundary conditions, after setting up the meshing, there is an element size of 20 millimeters after establishing the convergence, and an element size of 4 millimeter in structural details, and we establish the boundary conditions according to the NDGL and ABS classifications. Only simple supports are used, which restrict the movement of the rigid bodies and also allow for us to calculate the complete hull shock. So that leads to restrictions on the keel, right at the connection with the deck, Under its 3 degrees of liberty in terms of transition. At the mirror, we have 3 transitional points. And the calculation for the loads imposed on the model, we have those determined by the standard. In the picture to the right, we can see the distribution, the Islamic distribution, which is the most elevated pressure that was used in terms of the scantling and how that was distributed along the hull. We also included the deck, side, bulkhead, and mirror pressures. Now, as we saw before, the effect of aluminum on the model, we can see that for the plates, there is a boundary fluency stress of 123 megapascals, and for the profiles, 106 megapascals in the regions affected by temperature. After the structural model, we developed a model of analysis which allows us to identify the natural frequencies and the modes of vibration of the structure. This focused on the mirror, between the mirror and the first bulkhead, so that we can actually get to see the effects of the engine assembly and its operation on the vibration of the mirror and see how that affects the structure. And lastly, as we have said before, we are going to do a linear bending analysis to see if there is some stability due to compression loads all along the deck. Okay, for the results, we calculated the pressure obtained according to the standard and ISO 122.15. All of this with a wave height of 0.5 meters, which is recommended according to both classification societies. Okay, in all cases, we can see that deck bulkhead pressure is actually higher according to the standard. That's why, according to the methodology developed, we can find that the plate thickness is actually more conservative according to the ABS standard. Now, when we compare the difference between pressure and the difference between plates, we can see some differences in pressure and required thicknesses. The ISO standard gives more importance to the required pressure, while the ABS standard actually gives more weight to the separation between profiles and between transversal elements. Now, in the case of the bottom, although 3.7 millimeters of thickness is required, we decided to leave one, which is actually 25% higher thickness, to make sure that the regulation doesn't keep into account these aspects of the boat's performance with a possibility of abrasion because of the nature of the river in contact with the bottom. So we decided to provide additional thickness. The sides and the deck, as well as the bulkheads, were left at 4 millimeters. We did a similar operation for the dimension of the transversal section of the reinforcements. The standard is actually more conservative than those from the ISO standards. This leads to a situation where the computational model takes the dimensions, which covers both regulations for the development of computational model on the basis of the scantling results. On the basis of that, what we did was to verify the compliance with standards for different types of frames and different types of reinforcements, and improve in certain cases to maintain better resistance with lower weights. Okay, here we reach the second part of the methodology. We're developing the direct analysis. We compare the results of the ABS standard, which is the most conservative one, with some results obtained with the direct analysis, and in the majority of cases, and the evaluation carried out by the standard is actually more conservative. We have a value close to 2.2. The region of China has its own stress as well as low stresses. We decided to reduce the thickness from 6 millimeters to 4 millimeters of the plate. We evaluated and the stress don't go beyond 55 megapascals. And the reinforcement actually goes to the bow region where the thickness was left at 6 millimeters. Even so, as we could see, there are some regions where the direct analysis actually yielded security values that are lower than those of the standard. Okay, this is something we're going to discuss later on. At the corners of the connection between the side and the bottom, there are some concentrations of stress. In the initial model, we didn't include bars, which we can see in the lower left picture. This allows for better welding surface in addition to increasing rigidity of this connection. What we did is, since the standard doesn't consider these kinds of elements, we put that into the direct analysis. We could see that if we have a stress equivalent to 54 megapascals at the bars, and with the plates, it actually goes down. So with this improvement, we reach a stress that actually reduced down to 30% even with the 4 millimeter plate. Talking about the structures, we can see that the curved elements, the ones that are somewhat curved, actually yield the highest stress. We could see that from previous slides where there are certain places where higher stress rates are yielded as compared to the standard. The standard considers separation between profiles and frames and the property of materials and the pressure, but it doesn't really take into consideration the concentration of stress, which we could see all across the boat, where we can see stress concentration. Now, when we evaluate different points that we consider to be critical, particularly between the different beams and the frames with some kind of curvature, we could see that the beams supporting the girders, this stress is below 70 pascals. However, at the heel, with the connection with the beam, the stress can go up to 125 pascals, which actually reduce our fluency boundary for the plates and also considerably for the reinforcements. However, when we did the meshing and the detail meshing, we could see that those stress rates, in addition to converging, are not quite local. It's considered that what happens here is local deformation, which is going to relieve the stress due to a change of geometry, and there may be a case of hardening by deformation because it's very local stress and it's not considered to be a problem for developing the vessel's activities. To the right, we can see that there is an intersection at the deck of over 90 megapascals at the region with the highest stress, and that is not considered by the standard. The security factor is higher than the one found in this direct analysis. Now, when we map all of the regions with a stress higher than those recorded by the boundary provided by the standard, there are some points that we can see in the pictures, and in those points, we can say those points are local, which are not considered to be a problem for the operation of the vessel. Usually, these values don't exceed 140 megapascals, and as we said before, given the fact that they are so localized, we can consider that there is a plastic deformation, which is local, along with hardening due to displacement of the aluminum parts. Now, in the model, we also found some regions which, after applying mesh convergence, we can see that some of the values do not converge, but despite the fact that the mesh was finer, every time the stress actually grew. This means that the values are not real. They're not because of the concentration of stress or the vortices, but they are hard spots. They are peculiarities of the mathematical model. The most important one and the only one we found was the union between the bulwark and the deck near the bulkhead. Okay, the mirror is another area of interest because we've installed an outboard engine, and we don't want for those engines to make the mirror fail over time or at the first attempt. We've divided this into plates and stress with 120 megapascals. Taking into consideration that the vessel may be subject to collisions, the engines can be switched at some point, and there are some shocks to the bottom that may generate important loads on the mirror. We decided to leave the security factor. The security factor is about 135 with fluency rates at about 140 megapascals. In regards to the model analysis, 10 cases were run where we found 4 related to the mirror. The other ones, despite the fact that the model reported it, they actually displayed very low amplitudes that were not taken into consideration. This is related to the mirror, basically 4, related to the use of the engine, which is close to 22 hertz. We can see that the frequencies that come closer are number 2, mode number 2, that we can see in the upper right corner. And mode 2, which is 25% below the frequency of the engine. Here, we consider mode 4 to be critical, which is above the relay rate of the engine, and to operate properly, it has to go through all of these natural frequencies that we can see in the picture below. Now, according to the standard and the separation between profiles and plate thicknesses, we can see an allowable deflection near 4 millimeters, and according to the mode of vibration, only a deflection of 1.5 millimeters, which is not considered to affect the proper development of the vessel's operations. Lastly, we have the loads due to buckling, linear buckling, where we cover different modes of loads, and where we found that the most critical one is at the port side due to decompression of the deck. Now, we found that the multiplying factor is about 1.6, given the fact that it's higher than 1, and we can ensure that there are no buckling failures with the loads applied. Now, as a conclusion, we can see that the vessel complies with all of the requirements suggested by the ABS Classification Society and ISO. In the majority of cases, the requirements for scantling are more conservative for the high-speed craft standard from ABS, and that the direct analysis, despite the fact that in the majority of cases it shows how conservative the evaluations are on the basis of standards, there are some cases where they are more critical according to the direct analysis. This shows that there are certain cases where the considerations are actually far from reality. Okay, as we could see from the model analysis, we saw that there were no problems due to vibrations, and that the frequency is 15% above the relay, but with the deformations achieved, there will be no problems for the vessel. Okay, finally, and as we could see before, the vessel will not fail due to buckling or compressive forces. Okay, this is the end of the presentation. I would like to thank COLOMBIAMAR, the Navy, and SEAT for the support provided in the development of this project. Okay, I'm open to questions if there are any questions, Captain. Okay, David, thank you so much for your presentation. Quite interesting. Can you hear me? Okay. Okay, thank you so much for your presentation. Again, quite interesting. We can see that the work was very hard and technically significant. Okay, we have some questions for you. We don't have much time, but we're gonna have to tackle those quickly. Okay, how did you calculate or how did you consider the slamming? How was it dimensioned and what kind of criteria was followed? Okay, that is a very good question. Okay, as well as slamming is dynamic loads that depend on environmental conditions, wave height, movement of the vessel, the shape of the vessel at the bottom. But the regulations from the classification societies lead to different hull dimensions. The wave height established for rivers, which is only 0.5 meters, and on the basis of that, we are going to get some pressure values. However, those are conservative. The idea would be to actually come closer to what we can see in reality. Okay, perfect, thank you. Okay, is there any analysis that compares the percentage of overdimensioning in terms of the requirements of the standard and the simulation results? Okay, there is a way to determine how conservative the standard is on the basis of the simulation. From literature, we found some cases where the same thing happens. There are some cases where the concentration of stress is not taken into account by the standard, but a consideration of the standard as such to explain these cases, there's really nothing. There are some guidelines that indicate the way in which the model has got to be built, and we would have to see in which cases these things happen, but the standards are the only reference that we have. Okay, and also there is a question about whether or not in the modal analysis there is a criteria for determining issues that you were mentioning concerning propulsion and also the evaluation of the structure. Is there any criteria to define when there is a problem in this concern? Okay, the convenience of this model is that we can look at the natural frequency and the resonance frequency of each element and look at which ones are being affected. However, as we could see, there is a case where the natural frequency of some of the mirror elements is 15% above the relay frequency, which is yielded by the engine very frequently. Now, some of the criteria that we took is the deflections of the plate, of the profile. And we could see that that is below those indicated by the standard. The standard indicated 4.5. So in literature, we can find that above 10%, we would consider that there is a case of a coincidence. So it would be a case of resonance.
Gracias. Y por el tiempo ya solamente podemos hacer una pregunta más. Tenemos aquí una pregunta.
Okay, just one more question.
Si se ha considerado un análisis acoplado de PSI.
Have you considered analysis related to PSI? Have you considered an analysis in terms of GSI? I guess it has to do with hydroelasticity or something like that. Yes, as a matter of fact, we have a plan to develop an analysis of the effect given different wave conditions or environmental conditions on the vessel. This leads us to do a fatigue analysis, which we couldn't do here because we don't have any real loads. There's nothing defined, so there isn't much of an effect. Now, with this interaction between the fluids and the structure, we can have a load pattern in order to run a structure fatigue analysis and see which regions have been affected. Because we know that since it is aluminum, its lifespan is finite, and over time there are going to be cracks, particularly in critical spots. Okay, thank you so much. So this finishes your presentation. Once again, congratulations on excellent work presented today. It was also a very clear presentation as follows. We're going to stop for a few minutes and then we'll continue with the next talk, which is the third and last talk of the morning related to fluid interaction structure analysis of flexible propellers by Captain David Fuentes. Okay, Captain, thank you. Thank you so much, everybody.
Listo, muchísimas gracias. Perfecto todo.
Listo. Listo, muchas gracias.
Vale, vale.
Bien, David, muy bien, muy buena presentación, muy clara.
Gracias, capitán.
Hola, ¿cómo están? David, si puedes encender tu... ¿Quién es?
Hola, David, ¿qué tal? No te escuchamos, no te oigo.
Buenos días, mi capitán.
Buenos días.
David, ¿ya sentiste fragata? No.
Has done project that has worked as a vessel coordinator here in Costa Rica. Today he's going to present his work named Interaction in Structural Fluids Analysis Flexible Propels. Thank you, Captain. Good morning, everybody. Today, I'm going to present this work I've been working on since 2018 in Berlin University, analysis of flexible propellers from the point of view of structure. And what I want to provide is the progress according regarding flexible structures in order to improve the general performance of the propeller. During the design of this work, I could see how wonderful it is in the structural design, naval architectural, and I could see that there are two very important areas, very classical ones in this discipline, and this have to do with hydrodynamic and structure. During the development of the presentation, we're going to talk about history, art state, and the method and how the method has been used during the development of this work and the core of this research and some conclusions. So what is the interaction of fluids? Is the answer aligned? This structure has to do with vibrations, interactions when facing a load that can be hydrodynamic, thermal, or aerodynamic, and how the structural response affects the fluid. The fluid causes the deformation of the structure, and this affects the flow. And this interaction can be mechanical or thermal. For the case of our research in this presentation, the matching it was that we worked or were interested on is the mechanical one regarding nodal displacement and the structural domain, and the state of the structure depends on the loads, hydrodynamic loads that you put in the system. For the naval architectural area, this is known as hydroelasticity, and I want to mention some considerations, classical considerations that make sure that everything related to naval architecture, so that we can get to know the importance of hydroelasticity in the system. Normally, we know a classical approach in the design, and it has to do that the hydrodynamic loads have not to do with the structural component, but for the design of a propeller, the aerodynamic design considers that the propeller is very rigid, and on the other hand, the evaluation assessment of the structural resistance has to do carrying out in order to analyze the resistance an embedded both considerations are done separated. So what we find nice in this discipline is that it allows us to match the resistance of the structure and get to know more accurately how the structure will respond when interacting with fluids. Regarding state of art, we see the first analysis were made with hydroelasticity were carried out in vessels with in calm waters. We carried out in calm waters, and the Pringle phenomena was analyzed, in which resonance, global, and phenomena of was a vibration increasing one as a response to very rapid loads, like event of cover waters and submarine explosions. Regarding the propellers, since the end of the 90s, first hydroelastic analysis were carried out regarding propellers, and what they were seeking was to research the effects of deformation in metal propellers, in the performing of the propellers, producing a panel code and propellers with an AQ pronounced, And afterwards, in 2005 year, doctor, he was speaker, he was been cooperating a lot with the development of my research. Also, funnels code with finite elements to research how the research of the propeller affected in the 2008 year. Dr. Johnson integrated a big code with purpose of analyzing the propeller with compound materials that was designed to form and to get to know what was the effect and different alignings in the fibers when carrying out the deforming. She wanted to carry out passive deformation by different settings of the fibers, and she built this propeller, tested it in different aerodynamic interferences, and we could see how nice it was to have the facilities, your own facilities, to carry out this kind of test, because with your own facilities you can close the difficulties regarding research and development that we will be facing if we don't have the facilities. In 2012, there was an integration regarding all these topics to carry out optimization of rigid propeller and compare how the vibration behave. They're faced in different configurations. 2008, the response, the hydroelastic response obtained was compared using a different configuration codes, such as panels code, B code on fluid dynamic flow code, or fine code, with the purpose to get to know what were the consequences that the potential flow had in the results. It is important to mention that the potential flow considers the flow as an ideal one where there is no rotation. All the considerations that will allow to carry out quick estimations. And in the designing point, these simplifications affected the results. Getting more into fluid interactions in the structure, we have two main approaches: the monolithic approach, in which the solid and equations of solid and fluid are in the same mathematical framework and solved by the same algorithm. So as positive, we can say that the results obtained were more accurate than using the other approach in multi-physics problems. The inconvenience with this approach is that we have to develop very well the code for each application. We have to develop the code in order to carry out an integration in the two systems, in the equations in the two matrix systems. So it is required a lot of effort with less computational effort. So that for this application, we have to develop algorithms. So it's a more robust design. So the consequence is not very extended to its use. And for the other hand, the one that's more used considers the flow and the structure in domains of computational. Each domain has its own machine, and this machine is used for all its application for structure and fluids, and these two units are together by an interface. It is important to keep in mind that for this approach that's divided, it puts together items that have already been tested, that are robust enough, and that have provided good results, and that at the end of the day, the problem of integrating, keeping in mind that behind all these, there is a mathematical problem. At the end of the day, this problem, since many codes for fluid dynamics and finite elements that are very robust. The problem is the balance in the two surfaces. Regarding the fluid dynamic code, this code resolves the equations, the ones that solves the flow very accurately and considers the flow incomprehensible with pressure of the mass and the force, with this calculating pressure and hydrodynamic loads from the point of view of structure. The displacement equations are solved, and these equations are solved in the nodes, and the size of the matrix will depend on the amount of nodes and elements that are obtained. And this equation for the structural component contains the mass and matrix of the rigid edge, and for the model it also considers the effects of the hybrid mass and hydrodynamic spring. So
es el equilibrio entre el desplazamiento.
Looking for the balance between pressures in both sides.
En la interfase tenemos dos formas de estructurar la malla. La primera es malla ajustada.
The first is adjust the mesh, which is a procedure, harder procedure, since we have the mesh must be enough adjusted to coincide with the structural component and the fluid, and it's there where information transferring is carried out through the nodes. To carry out this kind of meshing is difficult. It has a high degree of difficulties. I mentioned each meshing. It's designed to obtain identification of each code. It's optimized to get information required regarding the component of fluid. And in the structural component, we have mesh that has a different setup because the requirements and need for each software is different. So this adjusted mesh is not very much used. But on the other hand, we have the mesh that's adjusted. Each mesh is used depending on the method it's being used. What it's done is that it's interpolated to transfer in the information to each domain. So in the bottom part of the slide, you can see what's happening in the fluid interaction. In the bonding of fluids, pressures are estimated, and these pressures are taken to the structural code. And in this code, we're going to have node displays, and in the structural component, we'll have deformation. The mesh will deform, and this deformation will transfer back through the interface, through the fluid mesh, and this one will read the deformation through different adjustment of the mesh. This mesh will deform, and then we're going to have a new surface to start over with the calculation. According to the coupling, we have one-way coupling. And for the coupling of one-way, we have two choices. One in which the deformation does not affect the fluid, but the fluid does affect the structure. So when we are working with the structure interaction work, we have a case offshore in which one structure receives the wave load, but the deformation produced by the wave, the structure is not taken into account for the flow, so the flow is not affected. On the other hand, we have the structure that's independent from the flow, but the flow is dependent. So as an example here, we have what happens when we provide the angle to produce the turn of the boat. To provide angle, the lines of the flow will deform, but what happens with the efforts are not taken into account. As for the coupling of two ways, we have the easiest one, that's number 3. We are going to find a balanced condition This is for a channel in which we have interaction with the water for any kind of obstruction. At the end of the day, this obstruction will find balance, the flow will, the deformation will be stable, and the weak coupling the deformation in the time, and this is used for air elasticity, and we have the strong coupling that's implied because we have different interchange of information in time, and this affects elasticity. Regarding flexible propellers, core of our presentation, and they're designed in nickel aluminum materials that are strong enough, as I mentioned before, hydrodynamically, the propeller is very rigid. It's rigid enough, so it's not necessary to think of deformation. To work with flexible propellers will cause some disadvantages. Advantages. You can save load. In literature, it is said that it provides saving of up to 50% of load. Less load, it's less inert in rotation, and less inert in rotation means less charge in the axle. So also we can. It's important for military vessels and research vessels and submarines. Surfaces that are flexible, not so metal, more and robust, with less noise. Besides, it is proposed, and this is the core of all researches carried out around this topic, to improve efficiency, general efficiency of the propeller. In point of design of a rigid propeller, the inlet angle of water, it's almost the same. Of out of this condition of design, we can say that we have more speed or less speed, and if it varies or coincide, and there where we have loss of efficiency in the system. What we are trying to look for in this case is where we are working on flexible propellers with materials, isotropic materials and homogeneous ones, in order to achieve that the passive deformation will be systematically in the propeller, and with this deformation we'll be able to achieve points out of the design conditions. Possible disadvantages is that we have maybe less structural resistance to impact the design. The manufacturing of the propeller has to be very careful in order to keep the homogeneity of the geometry and the pressures to be as possible adjusted to the geometry. We think that there might be erosion in the material or cavitation. For methodology used, a propeller was built. The material P812 is a polyamide, and the propeller printed was the one of P1790, and that's the opposite of the steady step of the PTC propeller. This one was chosen because the base mark one presented in the second symposium of International Maritime Propulsion in 2011. And this has gone through a lot of tests, calculation in fluids dynamic, and hence we have enough information that allows us conclude that all that we are doing with this method responds positively to reality. Characteristic features of the propeller, the ones you see in the slides, and the technique we use to paint out the propeller is the JF. And one considered two things. The one painted in plastic, the same that the one, the rigid one, and two, this propeller was not designed to deform. the methodology regarding interaction hydrostructure. We used the partitional one into components. One for the one for dynamic of fluids and the one for dynamic structure. The one for computational dynamic of fluids, we used the COLOMBIAMAR turbulence model to achieve progress coefficiency. With these coefficiencies, those were the ranges in which experiments were carried out, and the walls were modulated in the section of the tunnel, because we could see that when comparing the estimations, the results of the estimation carried out in the interaction structure fluid, comparing all that with open water, we have interference on the walls, comparing that with the results. So that's why we used the one of the tank, and in the first cell, we decided 90, and after carrying out a sensibility meshing analysis, we concluded that 1.1 million of cells is enough to get the results we are getting, and that they are independent according to the amount of cells. Regarding the computational component, we found, after carrying out analysis of MASH, enough for the result. We carry out to see the displacement and the coupling of the system in 2 days was implied compared to the coupling of the structural component using adjusted meshing, and also experiments were carried out to compare that the results we obtained in the computer corresponded to reality. And these experiments were carried out in Berlin University, in the tunnel of the university, with different advances, changing fluid speed in order to get the results we got. The torque was measured, the thrust, so that we got thrust and torque coefficient with different measurements, different times of the year, assembling and disassembling the dynamometer, and this to get different water temperatures, so that we can get to know that the results we got were independent of the conditions. Regarding the results of the experiment of the rigid propeller and the flexible propeller, you can see the estimation. We have, comparing these results, for the rigid propeller, we have differences 5%, 3 to 8%, and besides, comparing the results obtained with STAR CCM for the rigid propeller with this code was designed by him, and the estimations were made by from Lou, she's a colleague in the maritime dynamic department. And comparing the results, we have that they are very similar than the one obtained, and this allows us to conclude that with 3 different approaches, we have the same results, almost the same results. This provides reliability in the results. We are showing what's really happening in reality regarding estimations for rigid propeller and flexible propeller. What I mentioned a few minutes ago, the propeller was not designed to be deformed. If we see that there is an effect of the deformation in the general performance of the propeller, we have 3% of difference in the points that are not included in the design point. 1.4 to 0.8, it does.
5 minutos.
Gracias, capitán. En cuanto al análisis estructural,
Regarding structural analysis, we can say
para la condición más desfavorable, que es cuando
for the no favorable conditions, the progress coefficient is 0.8, 10.5 megapascals. This is not the condition. I must say the most favorable condition for the propeller when the progress advancement is part of a new simulating campaign that I'll be talking about later on. Also, it is important to mention that these calculations were made with ANSYS. ANSYS is a software very well known one for its quality regarding structural. What I did, I imported the charges, the loads, hydrodynamic charges or loads. And that's what's nice about all this is that regarding magnitudes, I got exactly the same results with difference of 3 or 4%, what shows that results are very reliable. Finally, and as a conclusion, the methodology was validated. The calculation was validated by experiments. We got the propeller that has a lot of information. That's the propeller P1790, P1 of Herisep, PPZ, and this propeller was not designed to deform. The effect P is a negative effect regarding general performance, but we know that what we expect is that the effect is negative because we're losing a lot of pitch in all of the conditions. So this opens the possibility for passive rotate adaptation of the propeller, and with this we can improve general efficiency. And very important is that with the comparisons that we were doing, we realized that the scale of the material, seeing that we need to find the right way to scale the material, because we found that using the same material in different scales, the deformation normalized when you scale the speed to go to vessel speed to model speed and RPS, you don't get a normalized modulation. So this is not in the presentation, but we found two possible ways to solve this situation. One is to escalate the model joint to lambda. This can take us, or this is going to take us to a more flexible material, with the problem that maybe the material that we find won't be reliable enough when we're going to print it, or to keep speed on the material and find our PCS equivalent ones that will allow us the deformation normalized one and have it equivalent. And I want to thank COLOMBIAMAR. I want to thank Maritime Dynamic System of Berlin University for support that they have given me in these 2 years and a half carrying out this research. And Rahul Suchet, Dr. Rahul Suchet, he's in this presentation because his support has been valuable, meaningful in this presentation. And thank you very much for listening. And I'm open to listening to your questions. Thank you, very interesting presentation. Now we're almost finished in the morning, so let's see. We have a few questions here. One has to do with the technique of solution in integrated structure, how the different tools are communicated in order to get the coupling results in an automatic way. there is an interface, Captain. This interface, what it does is transfer the results from one side to the other. And this interface reads the pressures we have in fluid computational dynamic and transfer those results to the surface. We have for structures, as I mentioned before, we have two domains and different ones that are combined or united, joined by this interface from the fluid to the structure and vice versa in order to change the results. And with this, generate interaction. What we want at the end of the day is after many interactions, we seek to find the balance in the pressure on one side and the deformation balance on the other side. Thank you very much. And one last question has to do with the turbulence model. It's to determine the optimal turbulence model. Yes, sir. I worked at the beginning when I was testing the software for my reports and carrying out calculations in order to get to know what was being calculated, if it corresponded to the propeller. I tried 3 different turbulent models, K omega, for example, and I carried out this K omega for all conditions that were tested. I was testing the propeller, the design condition was being tested, and that's the nice one because not so then for all conditions out of the design point with the best results were obtained with K omega ST. So at the end of the day, that's the turbulence model I recommend to use. Okay, thank you very much for your presentation. All everybody that's following us, we're going to have a recess and we'll continue to the afternoon to continue with the other presentations regarding dynamic vessels design. Thank you very much, Captain.
Listo, David. Gracias.
Listo, mi capitán. Muchas gracias.
Listo,
Sí, señor.
muchísimas gracias. Todo perfecto.
Bueno, vamos a almorzar, ¿no?
Listo, sí, señor.
Listo.
Hasta luego, mi capitán.
Hasta luego. ¿Qué tal mi cierre? Yo sí le doy más, le trato de... Le trato de darle más valor a la...